Welcome everyone to our Quantum Wednesday for this cold November morning, in New York at least. Thank you, Ioana, for joining us today. She will be presenting her ultra large scale compilation manipulation of quantum circuits with Pandora, which is one of their newer projects. So yeah, Ioana, please go ahead and screen share when you're ready, and take it away.
Yes, hi. Thanks for having me. Do you hear me well? And can you confirm that you see my screen presentation?
Yes, we can see and we can hear you.
Perfect. Okay, great. Okay, so then I will start. Yeah, so thanks, Vina, for the introduction. My name is Ioana, and yeah, I'm gonna present our software tool called Pandora. And some of these results were also in part due to a collaboration with Alan Robertson and Simon David from UT Sydney. And yeah, I'm just gonna start right away. So, okay, so first, why do we care about being able to manipulate ultra large scale circuits, and how do ultra large scale circuits look like? And the main motivation is that we will need to be able to have software that can process circuits of this size. And this is, for example, this is an older result from 2018. This is a resource estimation paper where they basically do the key counts for some Hubbard model simulations, and you can pretty much see that they quite fast go into the order of billions for the T counts. So these are some examples of practical circuit sizes. Now, as far as I know, some of these resource estimates have been improved ever since, but we are still most likely for most utility scale algorithms dealing with billions of gates. So there's a question of, okay, how do we even approach compilation for circuits of this size? So when envisioning such a tool that is able to process such circuits, we have kind of like come up with a set of criteria that we want our tool to be able to fulfill. And these criteria can be, for example, fast lookup of circuit patterns when we want to do circuit rewriting. The tool would ideally have multi-threaded access to the circuit, would have fast random access to the circuit, and it will be able to do all of this for very large circuits, right? So we're talking about millions or even billions of gates. Okay. So this prototype of a tool, or at least our prototype of a tool, is Pandora. So having this motivation that practical quantum circuits are ultra large, we need specialized tool and data structures that are able to process such circuits. And these tools should ideally be able to have some kind of caching going on at multiple levels of the compilation stack. And we should be able to also optimize these circuits that we are dealing with. And such a proposal is Pandora, right? So Pandora is intended as a full stack streaming pipeline. So the idea is that we only want to compile a specific algorithm or a subpart of an algorithm once, and then we want to reuse that partition. And the idea is that decomposition of a circuit in a specific gate state takes a lot of time. We ideally want to do that only once and cache it, and then we want to be able to store and operate on a specific partition simultaneously. So then from this, we want to be able to integrate Pandora into a stack of streaming compilers. And we also want to be able to, ideally, you want to visualize and manipulate the outputs of these compilers. So how do we store and operate on these circuits simultaneously? So how do we design such a tool, and how should it even look like? And our proposal is to encode circuits as directed acyclic graphs instead of the usual diagrammatic form, and basically put them into a database. So on the right here, you see what the diagram of a circuit looks like, right? So it's a CNOT and two Hadamards. You can take this diagrammatic form and convert it into a DAG. The DAG is the one in the middle here, where we have again the 2-qubit gate and the two Hadamard, two Hadamards and then some helper gates in and out. We don't need to go into details of what these are, but the idea is that this kind of representation, right, this DAG can be basically translated into a set of database rows, where each gate is a row in a database, in a relational database. And the advantages of such a representation is that we want to be able to operate on these circuits that we are storing, but we don't want to keep track of the qubit or the time slice or moment, depending on what terminology you're using when updating these gates, because that would take a lot of time. And we want to have a very straightforward circuit reconstruction. So once we took a circuit from Qiskit or Circ or whatever and put it into Pandora, we want to be able to get it back to Circ or Qiskit or whatever exactly as we put it in. So basically, we want to be able to do to go both ways with reconstruction. And I'm not going to talk a lot about the backend of Pandora, but I'm going to give some details. So the backend of the Pandora of our Pandora tool is PostgreSQL. So it's a database. And we wanted it to be a database because we want to ensure that whenever we operate on data, the data is consistent, even when we operate on it multi-threaded, in a multi-threaded fashion. We want to be able to store the data on disk, so we don't need to rely on RAM. We don't need to be limited by RAM for storage. And for example, a database can be more efficient than other types of files. Depending on what data types you use, can be more efficient than the JSON files. And as to why we chose Postgres and not any other relational database management system or maybe a NoSQL database, the reason is that we want to have a good performance with concurrent transactions. Postgres is widely documented, widely used. It has a very good documentation. It has advanced indexing, so there's a lot of configuration options and there's a lot of performance tuning that you can do with Postgres compared to other systems. So it just fit our purpose better. And on the right, you can basically see how what Pandora architectures, how the framework looks like. So up, it's basically a depiction of how threads would operate on the circuit. So you have a circuit stored in a database, and then you have a set of optimization threads. And then you have some other helper threads, for example, threads that read data from the database, reconstruct, or do any kind of cleaning to the data in the database, so on and so forth. And down here, what happens is that as a database, so Pandora basically has a Postgres server in the background. This Postgres server runs in a container, and depending on what we want to run Pandora on, it can be your laptop, it can be a supercomputer. You want to be able to have multiple containers, each running a Pandora instance and doing some kind of job that you want it to do. So basically, this instance from here can be any of these blue boxes here, and the purple box here is basically another Pandora instance that controls the other Pandora instances, right? So this is why we call this. This is basically it fits the MapReduce computational model. Okay, so what do we do with Pandora? So now that we have this database circuit translator, okay, how do we actually use it and what do we use it for? And we use it for a couple of things. The first and one of the most obvious tasks is to cache large circuits. Then we want to be able to decompose. Actually, we first decompose and then cache the circuits in the database. We want to be able to partition the circuits from the database and output them, stream them to another layer of the compilation stack. We want to rewrite the circuits, and there's also like a work in progress part of what we do, which is the verification of circuits. So we'll get into that in a bit. So let's start with the cache part. So as a cache, the idea about Pandora is that, okay, so utility scale quantum programs may occupy chasm files in sizes like 80 gigs. That's a lot of that's a lot of space that you need for a single file, and actually it's also tough to process. So this is a bit of an inefficient method of storing programs. So there's kind of a need for high-level classical management for program streams. And typically, this management system is termed as a quantum operating system. And on the right, you see such a depiction of how how basically the quantum operating system is controlling this quantum HPC hybrid. So we have this interconnect between the HPC and the quantum system, and we want to be able to execute large-scale computations with an improved latency and throughput. So the idea is that you would have some kind of communication between the quantum part and the HPC part in terms of classical bits, right? And these classical bits can come from mid-circuit measurements or simple control signals, but the idea is that you want to be able to do this efficiently. You want to be able to do this fast. So this is more or less what the caching part means. So we don't want to decompose a circuit all the time. When we want to run it on a computer, we don't want to decompose it on the go. Ideally, we have the circuit cached somewhere, and then we can stream it very fast. So this is why I will go into the decomposition now. So how do we do decomposition, and why it is important to do it and then have it cached in Pandora? So we take our ultra large circuits from different sources, such as Qualtron, Pilector, Circ, or Qiskit. And then we load these circuits as instructions to the Postgres database. And the streaming pipeline is kind of as follows. So we take a high-level block from Qualtron or Pilector down to a gate set, such as Clifford plus T. And we do this in a batched format, so in a streamed format. Then for each batch, we convert the gates of the batch to the Pandora format and then insert the batch into Pandora for caching, right? So we process it, insert it, and forget about it. We can reuse it whenever we want. It's like a way of preload operations and then retrieve them when you need them, with the decomposition only happening once. And the reason why we want decomposition to only happen once is here on the right. Are you seeing my pointer, my mouse pointer?
Yep.
Perfect, thanks. Good. So basically, we did some simulations for the Fermi-Hubbard circuits that I mentioned before. And then we looked at all the different stages of the pipeline that we have in Pandora, right? So we are decomposing circuits, we are inserting them into the database, we are extracting them from the database, and then we are partitioning them. And partitioning basically is the algorithm that decides how to take in which order to take the gates from the database and send it to the compiler. So basically, if you look here, partitioning is very fast. This is good for us. Extraction is fairly fast as well. So it's definitely faster than insertion, but now decomposition takes the longest. So we don't want to repeat these insertion and decomposition steps too often because it wouldn't make sense. However, whenever we are partitioning, we want to be fast, such as we are kind of here. So that's why we want to reduce the number of decomposition steps we need to take. And also, either
Can I ask a question?
Yes.
So I think I missed it early on, but the database is mostly used for caching or something else?
So the database itself, we also, when we rewrite circuits, we rewrite them in the database as well. So yeah.
And that's mainly used as like a lookup table in case you're doing it again, or?
It's like the database is basically, yeah. So the database, if you have a circuit, like I don't know, some kind of sub-circuit of RSA, which is very large, and you don't want to, the decomposition takes days and days. So decomposing such a block from Pilector or Qualtron, it takes days to do it. You don't want to do it multiple times. And the idea is that you put it into Pandora. Now, what you do in Pandora after it, it's up to you. You can rewrite a circuit, you can do a bunch of stuff, but the caching is just the part where you decompose. So Pandora decomposes the circuits, and then inserts them into the database. It's not necessarily a lookup table, but you can have the table itself is the circuit, right? So here,
Oh, yeah.
this thing, basically. So each gate from the circuit is a row in the database.
Okay. Okay. Yep. Sorry.
Okay, no worries. So yeah, please feel free to interrupt me anytime you have any question.
Is
So
it right if I ask a question before we move further because I'm afraid I'll forget? Is it all
yes,
right?
please. Yes.
Thank you so much. So my main question is, you said that we cache the decomposition of gates, so we don't repeat decomposition, correct? Great, that's okay.
Yeah.
So how would that work for like large scale gates like MCX? Is it gonna only work for a specific MCX, like for instance MCX with 4 controls, and only gonna cache that decomposition with 4 controls?
Yeah, so there's a limit with respect to the gate set that we can ingest in Pandora. So right now it's at most 3 qubit gates. Now we could do 4 or 5 qubit gates maybe, but the reason why that's a bit tougher to deal with is that you see here, basically for every gate that we have, we are keeping these connections as a column in the database. So basically now we are limited in the sense that we chose, okay, we're just gonna go as low as 3 qubit gates because we don't want to keep updating so many of these rows of these columns every time we rewrite the circuit. Now we can go to 4 or 5, but there's a limit. Like we cannot put, for example, not TOEFL, like controlled TOEFLs. We cannot put them into Pandora at the moment.
See, but I'm mostly wondering about like the idea of it, because like I was thinking, is it more like when decomposition is involved, there's like different ways of handling it. One is, for example, do you use primitive gates? Like for instance, do you always assume the lowest level is only U3 and CX, or for instance, do you get like a gate set for that you would sort of have as your lowest level? And so that's one of my questions. Is that it? Like, do you assume the lowest is U3 and CS for your case?
Is the lowest is what? U3?
So for instance, Qiskit, Circ, most of these usually assume a primitive gate. For instance, Qiskit assumes U3 and 6 are the primitive gates.
Okay.
Yeah, they don't have a definition. They don't have decompositions. Everything else is defined in terms of them. And decomposition is just going layer by layer down definition.
That's pretty much what we do. We actually use so we use Pyliter and Qisk and Circ to decompose the circuits. And basically we use because we take the circuits from Qualtron, we kind of use Circ and use the Circ decompose method to go down. Now the Circ decompose method, you can give it basically the gate set in which you want to decompose the circuit. So we don't, as long as they can decompose it, we do it too. But so we don't actually do the decomposition in the database. We do the decomposition at the Python level, and then we insert the batches. So, but as far as Pandora is concerned, as long as it's something that I can put into this format here, I don't really care if it's Clifford plus T or any other gate set.
I see. And it is one final question, because I have to go actually for Cirque's meeting. Um, is the general idea of Pandora essentially that you have some gate that's repeated many times, some high level gate, right? Not something like standard or low level. You have some arbitrary high level gate, and it's repeated many times. You decompose it once, store the composition in database, and then anytime you meet that gate, you just sort of load it from the database.
Yeah.
Is that the general idea?
Yeah, that's the general idea.
So why not just like store the chasm or whichever IR you use to store the decomposition, and with that be able to store like arbitrary size gate decompositions, as opposed to only being capped at 3?
So depends. So whatever you put into Pandora is more or less up to you. So the biggest circuit that we decomposed with Pandora had around 8 billion gates. I don't see how that would fit in a CASM file and how that would be processed. That's the only reason why we did it with the database, because we are really looking at circuits with hundreds of millions or even billions of gates. So we just wanted to see how can such a tool be able to process these sizes.
Is the 8 billion case resulting from like a really, really large number of qubits, or is it more like you have some control flow that's running like millions of times that produces that many gates?
So that was let's ignore the fact that we can reuse the decomposition of a block that keeps on repeating, and let's just do it. Like, oh, I have this circuit. I don't care about, I don't want to be able to, for example, so that was a case where we just wanted to see what's the total gate count of this circuit. Let's just decompose it. We needed it for some resource estimation where we didn't want to be concerned about tracking the inputs to the blocks and this and that. So we just decomposed the whole thing. So that's how we ended up with the 4 billion.
Understood.
But if you have really large algorithms, even these repeating building blocks are on the order of hundreds of millions. So that's why we.
Yeah.
Yeah.
Thanks so much. Apologies again.
No, thanks for the questions. Okay, so I believe I was here. So again, the Pandora insertion and the decomposition, this is basically a depiction of how many gates per second each step is able to process, and then we are the fastest is basically the partitioning. So that's why we want to be able to only repeat this part, right? And this is regarding your question. Yeah, these are some Clifford plastic gate counts of these Fermi-Hubbard circuits where we chose different basically different input sizes for the model, and the 100 times 101 was somewhere around 8 billion, something like that. So that's why we were also kind of like surprised that okay, we can go for scale with this. And this is basically just the relationship between the number of partitions and the number of gates. So how the number of partitions of the circuit increases with the number of gates. I will go exactly into how we partition in a bit. But the idea is that one of the largest circuits that we were able to transpile was, or a sub-part of it was Shor's algorithm. So basically, we took this from Qualtron, and we were interested in seeing how we can how long can we play this decomposition game. So what's the largest circuits that we can really decompose in Pandora? So basically, what we did is that we took the Shor high-level circuit in Qualtron, right? And then we were interested in what the final gate count, Clifford plus T, for example, or actually here we did TOEFL, C-swap, and rotations. But we were interested in, for this gate set, what would be the final gate count of it. And this is the control scaled addition block. So it's 2 layers down the decomposition of the full Shor algorithm. But the results are summarized here on the right. So basically we have even the creation of the high level instance takes a few minutes. But what really takes a long time is decomposing this lower level, this high level block to a lower level gate set. So for this single instance, so this is basically when you have modular exponentiation, you decompose it into a set of controlled modular multiplication, like some iterative modular multiplication blocks, and then each modular multiplication blocks decomposes into 2 controlled scaled addition, and this is the block that we were interested in. So it's 2 layers down the decomposition, and we wanted to see, okay, what the final gate count of this is for different bits for Shor's algorithm. So we did at most 1024. And we were interested in seeing how many gates per second can we process with Pandora for large instances, right? So you see that the gate count increases quite a lot. I believe it was around a few 100 million here. And down here, basically the number of gates per second that we can process decreases quite a bit as we increase the number of bits in Shor's algorithm, mostly due to the Python part of the code. But yeah, in short, we were able to go as high as this, and probably 2048 is also doable, but we didn't burn. It would have meant a lot of resources, because all of these simulations were done on the Lumi supercomputer, and since we parallelized the code, yeah, we're kind of like waiting for a reason to go that far, because based on some very preliminary simulations, this would take a lot of compute power to do. Okay, so circuit partitioning, I promised that we would go in through it. So a partition is an architecture-aware circuit partition.
Could I ask something about the previous part?
Yes.
Can you output the circuit as it gets processed, or do you need to wait until the end to give me back a circuit?
I can process the circuit as it gets decomposed.
Okay, cool, thanks.
Yep. Okay, good question. Okay, so basically, what happens here is that we are interested in compiling these circuits that we decompose to a gate set of our choice, usually Clifford plus T, and we wanted. This partitioning algorithm is basically leveraging some union find data structure and some Postgres very fast indexing happening behind the scenes. And this is an example, this is an example of a 2-bit adder partitioned into 4 components. So this is kind of like what a partition looks like. So given a number of qubits, a partition should operate on giving a T count and a depth of the partition as inputs, as parameters. The algorithm outputs basically these chunks right here. And we partitioned all kinds of circuits. This is a visualization of the fast partitioning with different parameters on a n equals 2 Fermi-Hubbard instance. So this is around 60K gates. And each vertex in this psychedelic thing is a gate. And basically the color gives you the partition. So these are basically when we vary these parameters that we give to the partitioning algorithm, this colorful thing is basically the partitions, right? So we did this. And the reason for doing this is that we want to compile our circuits that we take out of Pandora. So we decompose the circuits with Pandora, we cache them, and then we want to stream these instructions from the Pandora box to, well, first example is Cabalizer. So Cabalizer is developed at UT Sydney, and it's basically a graph state compiler. So what Cabalizer does is that it takes the partition that we gave it into Clifford plus T, and then it outputs such a circuit, the graph state construction and the scheduled Z measurements. And the idea is that this graph states represent stitchable abstractions of collections of fault-tolerant architecture compatible gates, hence why we partition based on some architectural constraints. And yeah, a Cabalizer can encode graph state circuits in very efficient serializable bit-packed structures. So this is one type of use for Pandora, and the partitioning was actually developed because Cabalizer needed it as an input. And the results are that Pandora is, so basically this was a paper that I believe we put out in July, where we were interested in seeing, okay, if you have the caching ability of Pandora and the compression ability of Cabalizer, so these two together, what are the speed ups that you can get? So basically, we were thinking that, okay, if you have a common an occurring sequence of graph state, you can cache and re-emit it. So it's ready for you to compile. And the idea is that when we take all the decomposition into account, we did adder. So we tried this for adders up to 2048 bits. And basically the full decomposition, if we were to decompose from scratch every time, it would take on the order of 4 minutes, I believe, 3-4 minutes. But when we are partitioning, and when we cache and just partition, basically we are significantly faster. So it's somewhere under a second. And then same with Cabalizer, the full graph construction takes a while, but then once you are having this compression, basically you can you are allowed to decompose and construct all those graph states required to implement the 2048 bit adder in less than a second. So this is the type of speedups that we were interested in obtaining with this merging these two tools. And we have our own, like our in-house lattice surgery compiler too, called the LSC compiler. I believe this was actually developed with unitary fund with a micro grant. I hope I'm not making this up, but the idea is that the same process, we decompose and generate a circuit in Pandora, and then we partition it from Pandora, and then we send the instructions to the lattice surgery compiler, and yeah, we generate such things out of the lattice surgery compiler. So this is actually another project happening in our group. A colleague of mine is developing this Minecraft visualizer. So this is basically a Minecraft video of what the output of the lattice surgery compiler looks like. Yeah, this was more of a fun slide, but yeah. We are basically visualizing the space-time diagrams in Minecraft and hitting them with our hand. Okay, and then another part of this whole stack that was interesting to do with Pandora is rewriting. So we are interested in doing some kind of template-based rewriting on the circuit that we are caching. So basically, we never need to get the circuit out of the memory completely, right? You have this huge circuit, then you want to maybe rewrite it in some sort of way. It doesn't really matter how. But the idea is that you want to be able to operate on it while you are storing it. And we have these parameterized rewrite rules written in the form of stored procedures in SQL. So the rewrites are applied in parallel on the stored circuit, and the database ensures correctness with a bit of care from the programmer side. But basically, we can operate on the circuit in parallel with multiple threads. And each thread is doing such a rewrite, right? So maybe it has some single qubit or 2-qubit gate cancellations. It has some Z commutations with the control of some C0, or maybe it has some X rotation commutation with the target. It has some actually, this is a fusing. These are some fusion rules. And we also do such things like reverting the direction of the C0. We also have Toffoli gate decompositions and so on. So things like this, we were interested in implementing them. And we benchmarked Pandora. So you would think that because it's a database and most of I mean, when you're operating on it, it's stored on disk. Only some specific parts are taken into the main memory, but you would think that it should be slow, right? I mean, it would never be able to beat, in terms of rewriting speed, a common optimizer or a compiler like Qiskit and TKET, because obviously it's not in memory. But we did some benchmarks, and we were quite surprised too that whenever we only care about speed, we actually do get some performance benefits. So we did this kind of synthetic, these kind of synthetic benchmarks, and we call them synthetic benchmarks because it's not a useful circuit, it's just a circuit that has some properties, and we are interested in seeing how fast we can rewrite the circuit with those properties. So what we do is that we generate random circuits with n C0 gates. The C0 gate is missing, but it's n C0 gates. So it's from 10,000 to 100,000 C0 gates. And then we choose a probability P, which varies, which is we choose three types of three probabilities, is 0.1, 1%, and 10%. And we flip PR times n C0 gates using this rule, right? So the reverse of this rule. So we take a C0 and then we reverse it. And then what we are interested in doing is for these probabilities, traverse the circuit from left to right and just flip them back, right? So just make them as it was before, and then let's benchmark and see who out of TKET, Qiskit, and Pandora can perform better, and how does this how much the probability of occurrence for such a template influences your results. We were also interested in this. So now Pandora can run single-threadedly and multi-threadedly. So every template that you have, you can run 16 threads that try to optimize that specific template. But of course, it should be a fair comparison. So we did a single-threaded benchmark against TKET and Qiskit, which are also single-threaded. And basically what we get is that for 0.1 and 1%, Pandora manages to outperform. And when we get around 10%, I believe that Qiskit manages to be faster by a bit, but the intuition behind it is that whenever we have some templates that we are trying to look for in the circuit and the templates don't occur that often, actually Pandora is faster. And the reason for it is that when we are rewriting with Pandora, we search for the templates and then it's like we jump over to them. So jumping means that we have some efficient data structures that allow us to search for these templates fast. Whereas in the Qiskit or TKET case, we literally have to go gate by gate and be like, is this the gate that I'm looking for? Yes or no, but I'm moving to the next one. So this performance model, and the reason why our intuition is that it's faster with Pandora is because searching is implemented. It's a database, so it's optimized for this. It's not that much of our merit, but it's basically Postgres doing its magic behind the scenes. And then, of course, it's a database. The reason why we put the circuits there to begin with is that we want to have multi-threaded access to it and rewrite them. So we did some simulations where we were interested, okay, for this same rewrite rule, I don't know, add from 1 to 16, right? So from 1 to 16 parallel threads, which aim to find this template and rewrite it. And basically, this is the speed up that we get, right? So this is the number of threads that we add, and this is the speed up that we get when doing so. So there's an advantage of doing things, rewriting in parallel in Pandora. Now, the speed up is not perfect because we have some communication overheads between some locking, there's some synchronization overhead that happens between the threads. So it's not going to be perfect, but we are going to get almost a perfect speed up when we are, for example, decomposing circuits. So whenever we want to decompose a circuit, we don't just go gate by gate. We actually take the circuit and kind of like look at the blocks it's composed of, and then we have different threads decomposing different parts of the circuit. And basically, the more threads you add, obviously, this is an embarrassingly parallel speed up, right? So you just add more compute power, and then of course we are able to decompose these subparts of the circuit in parallel and insert them at the same time in Pandora. So actually we're not that worried about, I believe that the 8 billion gate circuit, it took around 10 days, I think, the first time we did it in Pandora, because it wasn't multi-threaded. But when we added the multi-threaded, when we parallelized the code, it was something like, I don't know, 9 hours or so. So it was quite fast. Okay, and non-synthetic benchmarks, of course, when it comes to speed, we might be faster, but we also care about if this is an optimizer, or if we view it as an optimizer, what is the performance at this stage? So we have a very straightforward optimization heuristic. We just choose these templates, the templates that I showed you before, and then we run a bunch of threads performing those circuit rewrites, and then we control the frequency of the rewrites by the number of similar parallel threads. And then we benchmark them on up to 2,048 adders, and then we recorded the results. We were just like, okay, if I'm not doing anything smart here, if I have no heuristic whatsoever, if I just let these threads run, what happens to my circuit? Does it make any sense? And we were comparing with this paper from a few years ago where they have some heuristic for which they optimize, and they are interested in seeing the T count reduction. So we also recorded the T count reduction, and we have some kind of reductions, I don't know, starting from perhaps 9%, the most, I guess, for this 64-bit adder. And we also recorded how the specific gate counts we were interested in varies in time. So I believe we let this run for 100 seconds, I think, and we were interested in seeing, okay, if I let it run for 100 seconds, how is it going to reduce anything? So maybe it's not really visible here, but it's reducing the T count by a bit at the price, right? At the cost of increasing the number of Hadamards, because this optimization, it also adds gates to the circuit. It doesn't only delete stuff. So it has to be able to commute the T's such that they cancel out with some T daggers or things like that. So, or maybe it's fusing them into an S gate or so on and so forth. So basically, and I believe this is obvious here because the S count increases for this, maybe in all of the cases. So yeah, this is a type of non-synthetic benchmark that we did. And the last bit of my talk is verification. So what do we mean by verification? Well, we were interested in seeing if I have two circuits, and C1 and C2, and I'm interested in seeing if these circuits implement the same unitary. Can I do it by applying rewrite rules? So this is not our idea. This is not necessarily a novel idea, but we were interested if Pandora is able to apply these rewrite rules in a way that actually verifies something. Like you are interested in seeing if these two circuits are logically equivalent by basically doing something like I have circuit C1 and then I take its conjugate transpose and then I insert it into the database next to C1. And then I want to optimize, I want to apply rewrites until I get identity. So the idea was that we wanted to see if the speed, so this is just a speed verification benchmark. So we wanted to see if you have Pandora and you have these two circuits, is there a way of applying rewrites completely random? So you have no idea what you're doing there. But can you verify that the circuits are the same by reaching identity? And this is the way we did verification. So it's basically just benchmarking the speed of Pandora, which is the dark blue line here, for the purpose of implementing an equivalence checker. So what we did, this is again some kind of synthetic benchmark. So what we did is that we generated 10 random circuits and with 32 qubits and 27,000 gates, and then basically measure the time it takes for Pandora to verify the equivalence between two circuits, and the time it takes for the MQT.QCEC tool, so the pink line, to show non-equivalence. And I believe MQT has two types of checkers here. It has the ZX checker, and it also has the decision diagram checker. So we benchmarked with both, and we let all checkers run with a timeout of 1,000 seconds. And we benchmarked both for equivalence and non-equivalence. And the way we did it is that we took circuit C1, and for equivalence, we just took the conjugate transport, so basically the inverse of the circuit, and then we put them into Pandora, and then we waited. We let some threads run that cancel CNOTs, and we waited to see how long does it take to reach identity. Does it even reach identity? Is it gonna work? And then when we wanted to benchmark non-equivalence, we took C1 and then its inverse, but from the inverse, we removed some gates at random and wanted to see, okay, this is also, I believe, was benchmarked before, so it's not a new idea, but the idea is that if you know that there's no way you're gonna reach identity, how long does it take? Does it make any sense to do this? So basically the ZX checker, I believe, timed out before deciding in the case of equivalence. The Pandora non-equivalence checker method is of course probabilistic. So the way we did it was like, okay, if it takes us way longer than it would be to verify equivalence for these circuits, then definitely it's probably non-equivalence, but we might be wrong. So it's probabilistic. And actually, we were surprised that equivalence never timed out, and it was also quite fast in most cases. Yeah, and this was a multi-threaded basically rewriting. So we were just basically looking for patterns in the full thing that can cancel out such that we eventually reach identity. So this is a type of benchmark that we did. Now, of course, if you are doing verification with two circuits that don't look the same at all, and they have a completely different structure, there would be a bit of would need a bit of work here to figure out how algorithmically how we would perform the verification. We might need to commute, for example, all the t's somewhere and be able to cancel out bit by bit. So it would be a bit of a different, a more complicated procedure. But here we were interested in, okay, pure speed. How do we do it? And yeah, I reached almost the end of my presentation. So this talk was based on 2 papers. First is the main Pandora paper, and the second is the collaboration with Alan and Simon from UTS. And takeaway message is that there's a lot of questions that I get. Probably I'm not also making this, might be my own fault too, but a lot of people are kind of like confused. Okay, but what is Pandora? So is it a rewrite engine? Is it an optimizer? Is it a compiler? What is it? And my answer is always that actually it's a rewrite engine, but it's a tool that it's not actually built for a very specific tasks, because it works at multiple levels of the full stack compilation pipeline. So it works in a streamed fashion. It's HPC friendly and hardware agnostic. So you don't need to worry about Postgres because everything runs in a container. It's fairly simple to install. But the idea is that it's not built to act just as a transpiler or just as an optimizer. I think because it's so scalable, it's useful at multiple layers of the stack. And ultimately, it is a Pandora box, so it can store representations of quantum computation and operate them on them in a multi-threaded fashion. Yeah, okay, I'm done. Thanks. Are there questions?
I think there's a question in the chat.
Okay.
Maybe can...
Yes, looking for it. The only found it finally. Okay. How is non-equivalence checker scheme different from equivalence check scheme in terms of logic implementation mechanism? So when it comes to logic, it's the same. So that's why we said that non-equivalence is going to be probabilistic in our case, just as it is in other checkers, because non-equivalence here, it would be a bit tougher to say for sure, okay, there's no way this is going to be equivalent because we just have a very long timeout. So basically what we do is that Pandora tries to keep on canceling gates and reach identity, but if it didn't reach after a specific point, we can kind of like agree without looking into the database, okay, this is probably not going to be equivalent because we're not be able to reach a conclusion, right? So this is going to take forever to run, kind of like that. So it's probabilistic, and it's very preliminary. It's not something that it's not a fixed. It's not entirely reliable in this sense, right? Maybe if you have real life circuits, the process of commuting gates to reach eventually a cancellation can take so long that you wouldn't be able to. Maybe it would be a false negative. What is the bottleneck in this stack? Be it compute, database performance, memory. Which one would you want to cluster earlier? Which one at a later stage? Good question. With the risk of sounding, yeah, I think I believe that the circuit decomposition times take a lot of the total time it takes to actually compile these circuits. So as you've seen, also for Pandora and Cabalizer, a lot of it was genuinely getting these Qualtron high instance circuits decomposed down to these gates that we are interested in. The main whole code base is in Python. Yeah, I believe this might be one of the issues. The fact that we are relying on a lot of code that doesn't depend on us, and yeah, we tried our best to parallelize it, but in a very like embarrassingly parallel way. So there we are always going to be kind of like bottlenecked by this. But of course, there's a lot of database performance Memory, I believe, yeah, Postgres is absolutely amazing. I'm absolutely amazed by how amazing Postgres is. It's just I could never imagine I can squeeze this much performance from a database in these kind of tasks. So, because we also compared with TKET and Qiskit, I believe, after they had their backends rewritten in Rust. So we were actually, I forgot where my own slide is, but we were quite surprised that Pandora can outperform even for these rarely occurring templates. But apparently the fact that we can search fast for patterns, that would be my answer.
I have an additional question about this slide in particular. So
Yes.
I want to understand more. What did you, after you find the instance that you need to rewrite? Because I understand how SQL will be very fast at finding it. But I'm not really seeing the reason why you would be outperform after a certain percentage of rewrites needed. Are you bringing it out into Python and computing in Python and then putting it back in? Because in theory, the impression that I have of SQL is that the rewrite itself should also be very fast if you're doing it in a database. No?
It is, yeah, it is it is actually happening in the database. So we don't
Oh,
bring
it is happening.
It is happening in the database. So we don't bring absolutely anything out of the database when we do the rewrites. Everything is written in this SQL code that just basically updates these rows based on how we told it to update the rows, right? So it should be a valid rewrite, circuit rewrite, but everything happens in the database. And the reason why around 10%, maybe it starts being a bit slower, it's because all of a sudden we don't spend as much time searching. We spend a bit more time actually updating the rows. And the thing that happens here is that Qiskit and TKET, and they don't have as many checks that happen behind the scenes. So the database needs to check a lot of stuff when you do an update or when you do a delete, when you do an insert. There's a lot of things that the database checks behind the scenes. Like, is this the good data type that you added on this column? Is this the this and that? And when you have that many, because we did it for like 100,000 gates, right? 10% is 10,000. When you do it so many times, you don't really see the benefits of the search anymore. It's really you're starting to get a bit slower because than you were before, because actually, the search gave you a huge advantage.
Okay.
Yeah.
And the second part of the question that I have for this is, if instead of actually putting this back in the database, you give me the rewritten version, do you think that would further lower the speed, or do you think that would make it harder?
So you mean you want me to export the circuit to you while the optimizer keeps on rewriting the circuit?
Yes, exactly. So I don't want you to put it back in the database because I don't need it anymore. I want you to give me the rewritten version.
Yeah, that's shouldn't be too much of a problem, because if you remember, there was this thing here. So actually, the optimization threads can run while I read out of the database. Now you're gonna have some specific view of the data that was in the database, but yeah.
Okay.
But I don't see why you would ever want to do this, because I assume that you wouldn't have an issue optimizing the circuit that's stored anyway in the database and then extracting it when you're sure that, I don't know, maybe your optimization converges to something that you're fine with extracting. But it might be just me.
No, that makes sense. And then the third part of this question is, and I think I already asked it like a couple months ago. The rewrite rules that you're currently using are sort of hard coded into your program. There is no parameter where I can give you a couple of rewrite rules to apply, right?
So in the sense of if I okay, so are you asking if I need to actually write the code for every rewrite rule in particular, or if when I run the
No. I'm more asking whether I could give you an arbitrary rewrite rule somehow as a parameter for
Yes.
Pandora to do this, for Pandora to do this in the circuit and give me like the rewritten version. Even if the arbitrary rule makes no sense, I just want to know if the computational capacity is there to like do that.
So we don't have an automatic. So actually, this is something that I would be very happy to do. I haven't because of probably lack of time, and it would be a really fun thing to do, to be like, okay, there you go. You have this rewrite rule that's not in the library of Pandora. So, but you want to also try to test that rewrite rule. Can you please translate it from Python, so to say, to the SQL code that is needed to actually implement that rule? This is something that we don't have yet. I would love to have it. So yeah, it's definitely something that I'm kind of like looking forward to do, because we don't have it yet, and I think it's very needed, because right now we only have these rewrite rules that you are seeing somewhere here. So we only have these ones where here we have the ability to parameterize this theta, but these are the only types of rules that we have. And I believe Alexandru is actually working. There's a colleague of mine working on some TOEFL-based rewrite rules, but that's about it.
Cool. Yeah, thank you. That would be super fun. I agree. It looks very cool. Cool.
Yeah. I see another question in the chat. So, how large of circuits have you tested, depth and qubit count, and have you compared performance in terms of reduction in number of gates at the end of the circuit optimization? So the largest in terms of depth, we never counted the depth. Only the gate count of these circuits that we have tested. So yeah, the largest one, I believe it was, I think for some Shor instance, it was about 20 billion. For some Fermi-Hubbard instance, the largest one was 8 billion. But in terms of depth, I have no idea. I've actually never tested, okay, what would be the depth of this circuit? I haven't. Because we only check the depth on the partition that we extract, right? So that's where we are interested in seeing, okay, because the depth is an input of the partitioning algorithm, then we test. But for the full 20 billion circuit, no, we haven't. Qubit count, I should know this. I could check it easily. I've got this question before, and it seems like I'm again unprepared for this question. I have no idea how many qubits at the end. For some of the circuits that we decomposed, I would have to count, but I cannot tell you off the top of my head. Whatever Faltron gave us, honestly, because for example, an input gate. So, for example, the beginning of a qubit and the end of it. Basically, it's like you initialize and then you measure, basically are these type of gates. So we can find out how many of these we have quite fast in the database, but I actually have no idea exactly to tell you. And reduction of number of gates at the end of circuit optimization. Yeah, this was the only experiment we did in this sense. It was this other experiment, right? So where we recorded the T count before and after, and this was the amount reduced, like we reduced the T count by 8%. But we didn't actually try to optimize any of these circuits that more like super useful circuits. We didn't actually try to optimize. So I maybe I forgot to say, and I should, these adders that are implemented in this paper, they are highly non-optimized, right? So they are like adders that you would get out of Culture and ICM are already quite optimized by hand, and I don't think Pandora would maybe not get much of a benefit after that. I haven't tried it. Okay, so when working with Qiskit and tools like Pandora, how is the performance of quantum circuits evaluated or benchmarked, especially compared to their classical simulations? So if this goes, so Pandora is not a circuit simulator. So I don't know what to tell you here. But what I can tell you is that when it comes to fault tolerance, we are looking into ways of rewriting. So this is very like sneak peek, but we are looking into ways of rewriting circuits, syndrome extraction circuits with Pandora, such that maybe we get we get some reduction in terms of the hooks. We are looking into how, so we want to maybe see if I have this circuit and I rewrite the circuit in a specific way, am I improving my logical error rate? Something like that. So we are looking into these kind of things because you can also see Pandora as a search engine, right? Like we are trying to rewrite the circuit in that such that the circuit would ultimately maybe fulfill some criteria that we are interested in, and this is something that we really try to look into. But that's why I'm in an endless learning steam curve. It's a very steep learning curve for me right now because we are trying to kind of like integrate with Steam and see. I rewrite the circuit, I take it out, I put it into Steam. How does it perform? Something like that. Yeah. I hope I answered all the questions. Please ask me more if you have more questions. I'm open for discussion.
Yeah, I think that's all the questions in the chat. There are more questions from the audience. Feel free to unmute yourself and if not, I think we're also on time. Thank the speaker very much for the great talk, and yeah, thank you everyone for joining the talk. And I think it's end for the seminar. Yeah, thank you all very much. Yeah,
Thanks so
thank you,
much.
Ioana.
Thank you.
Thanks a lot.
Yeah.
Thank you. Bye.
Bye, everybody.